Okay, welcome everyone to our Friday, September 6th edition of Consensus. And we're going to be talking about the RCast, the most recent RCast. And Isaac, take it away.
All right, cool. So, like I said, this is my understanding of what was discussed in the RCast. Not an expert, would never claim to be. With that being said, my understanding of what we were doing there is trying to present a generic way of constructing terms. So, trying to present a generic term constructor essentially, in the sense that once we've constructed these terms, we then have something that is closed under reflection. And so the way that I see this happening is basically he's taking some kind of, he's calling it a polynomial functor. You can think whatever you want when you hear those words, but the fact of the matter is you have, n places to kind of like put some kind of term constructor or name or process or something along those lines, and that's kind of what these different powers of X are representing there. I don't remember exactly what this K was all about, and it doesn't specifically say here, so I'm just gonna kind of overlook that for right now.
What about little x? Is that a multiply?
Oh, yeah, I think, maybe like a cross product or something like that. But yeah, like multiply basically. And then what he's doing is, so he's got this kind of like formal polynomial, and he wants to take, a derivative, like a formal derivative of this thing. And so, he's got the equation for the derivative here. And then basically, my understanding of the importance of that was kind of like, we now have some hole that we've punched in these different terms. So the T, I think, is coming from the fact that we're trying to build terms with this particular polynomial. And so taking the derivative kind of like punches a hole in the sense that we had this ith power that now all turns into I-1 powers. And so now we kind of have this placeholder, like a context essentially for our terms. And so then he's using this derivative that we just took for this, term constructor T, and then filling that hole with a name. I don't remember the importance, like why did we choose names over processes or something like that. I don't remember the reasoning there. But essentially that's the idea. So we started with this, this polynomial for constructing terms in the sense that like this thing is some n-ary term constructor, so we can put n, different processes or names or whatever we want into these variables x, I. And so having taken the derivative kind of gives us these contexts, and then we want to fill these single hold contexts that we just created with names. Like I said, I don't remember why that name part is important, but that's kind of the idea. And so then once we fill these holes with names, we now have some new term that we're constructing. So we're calling this T prime as opposed to the T that we originally started with. And then he was talking about needing some sort of name management mechanism. And so using something like the lambda calculus as our name management mechanism. So we can do, application of these terms and, abstraction and that sort of thing. So that's what this like ABS is like abstraction, APP is like application from lambda calculus basically. So he's calling this new, and the other thing is, usually when we're looking at some sort of grammar for syntax, it's usually in BNF form, but he's using some kind of domain equations to express essentially the same idea. So you can kind of convert all of these equations that are written here into something like BNF. But either way, so what he's saying is this this lambda thing that we're constructing here is going to be all of these names that we originally started with. That's right, I can't select these. So it's going to be all of these names that we started with, and we can Reify, I don't remember exactly the right term, evaluate, whatever you want to say, put a star in front of these names, right? And they turn into processes, just like in ruling.
I want to start the recording. Can you just give a sentence on what we're talking about?
Oh, I've got it started, Jim.
Oh,
I started at the very beginning, so we've got it all recorded. Yep.
Awesome.
Yeah. Well, I mean, like, I haven't seen much of his computational calculus classes, so I feel like I'm kind of out of the.
Yeah. Okay. Maybe I can just like explain some of this domain equation stuff. So I mean,
even just the first one, like kind of better understanding what X is. You said it's a term constructor.
Yeah. So think of X can be like an integer or something like that. And so what we're saying, and it can be like the type integer. So you can put any integer you want in there. So just looking at this first term, like this T of KX thing, basically what we're saying is we have n different places to put an integer. So like maybe 1 is one of those integers and maybe -10 is one of those integers, but we have n places that we can put integers basically. And then this KI thing, like I said, I don't remember exactly what it is, but maybe it's some sort of way to like augment these integers or to like wrap them in a certain way. Like maybe I want to make a set of integers that has like n different integers. And so like these k sub i's are like a set wrapper or something along those lines.
Okay. Yeah, because unlike if this were just integers, the summation operator really just defines that it's a polynomial, but you can't actually add to.
Yeah. So this sum is really a coproduct in like a category. So it's exactly the same thing as the pipe in like a BNF presentation. It's identical. So you can translate from one to the other. And this is just like a really seductive kind of way of writing it because it looks like it's really familiar, but we're really talking about coproducts and like, okay, yeah, it resembles a polynomial, sure, but what does it even mean to take a derivative when we're talking about some polynomial functor? It's like, yeah, you kind of like abstract over the idea of like what we typically mean by a derivative. Yeah, but that's kind of the rough translation is like anytime you see a sum, we're really talking about like an or kind of construction. So each one of these terms can be, how am I trying to say this? So
considered part together.
Yeah, something along
X
those
could
lines,
be just
right?
kind of like a process in rolling.
Yeah, so X could be like a process, exactly. Yeah. Yeah, and then, like, what does it really mean to be multiplying by this number here when we're talking about like a term constructor and a term? I'm not really sure exactly, but like I said, I'm definitely not the expert on that stuff. So like the whole idea then is we have some kind of generic way of constructing these terms from whatever, functor, which is basically just like combining these different kind of subterms that we have. And then, so we're specifically adding these names to these contexts. And like I said, I don't remember why the name is very important. But now that we have these names added to our contexts and to our term calculus, we want to have some sort of name management, over these terms. And so he's using something like the lambda calculus to do this. And so basically we're saying this grammar or syntax or whatever we're building here that we're calling lambda, it's parameterized over this k and this x thing. But it can come in basically 5 different versions, right? So there's like, evaluating a name. So just like in ruling or RoCalc. We can do abstractions that will first take a name and then one of these lambda terms. So just like from lambda calculus, where now our variables in lambda calculus are basically playing the same role as the names in this one. We have application, just like before. We need some sort of, so we have an application. So this is interesting. So saying application is going to take a name and a lambda term and then another name. So we want to, so why does that make sense? Because typically when I think of application in lambda calculus, it's just any two lambda terms whatsoever.
Right. Yeah. Why does it take a name?
Yeah. Yeah, I'm not sure. I was wondering if maybe it's because, maybe there's a typo here. I'm not really sure. I remember there being a typo somewhere, and I don't know if it was corrected before I got these slides. But either way, I'm wondering if, so this is taking a name and a lambda term just like this abstraction is. So I'm wondering if they're thinking like this first thing that the application takes is an abstraction, and then it's going to take a name basically into the abstraction. I'm not sure if that's what's going on here. And then they're also including all of these terms that can be built by T. That's the original thing that we had here. And then also all of these terms that can be built with this T prime, which is basically like all of the context that we had from the original term calculus, and then with those holes filled in by names. And then our names that we're talking about are just quoted lambda terms, just kind of like in a similar relationship as like the processes and names in RoCalc or in Rolang. And then he's taking this reflective closure, which is basically, the thing that satisfies this very last equation here, this R equals lambda KR. And basically that's saying just take the set of processes to be it means to take the set of processes such that all of the names are only quoted processes, or it's to say to take your set of names to be only the quoted processes essentially. So don't introduce like anything else basically. So this is essentially the construction that's done in the row calculus to make it reflective, is to, not have anything from outside, like, with the pi calculus, there's just kind of like an infinite set of names that you can choose from, and that's kind of canonically given. Whereas in the row calculus, we start with some set of processes, which are basically just built from the stops process, and then this notion of names. But where do you get names from? Well, you get names from quoting processes, essentially, right? So like once you have one process, then you can form some names. Once you have some names, you can form some more processes, and it's kind of a recursive structure.
Can you give an example of that? I don't really see how you get from names to more processes.
Yeah. So you can always start with the stopped process, and I'm assuming the stopped process is coming to us here. If we took in this capital T, the first thing, if we were to take 0 of these, like an empty sum, basically, I'm assuming that's the stopped process. It's the typical kind of idea from the pi calculus. So once we have one process, we can form a name, because a name is basically just take a process and quote it, right? So once we have one process, we can form a name, and once we have a name and a process, we can start combining them in different ways. So like once I have a name and a process, I can then send that process on that name, or receive on that name, and then have that process as a continuation, that sort of stuff.
Interesting.
Yeah.
Okay.
Yeah. So does that make sense? You guys have questions? I don't think I'm doing like the best job of explaining this, but hopefully it's making some sort of sense.
Well, I actually did get sort of a mental leap with your explanation. I think I'm further along than where I was. So just getting the idea of, rewrite rules and, why are we going through this whole exercise? I have a better understanding of from that aspect. So,
cool.
Yeah.
So the row introduces the new, right? So how does the new fit into this?
That's a good question. I'm not sure how, so you're talking about like a new name declaration, right? Like how do we bound variables once they're free, or something along those lines? I'm not 100% sure. Well, so how do we get new out of the row calculus? This is something I'm still not 100% clear on.
Yeah, I feel like it breaks the rules.
Yeah, my understanding is that, so we don't need replication, and that's I've seen that construction or the encoding of replication into row calculus, and basically the idea there, which I think is pretty cool, is so since we have like these sends and receives, right? We can basically just make a process in such a way that we'll send it and receive it at the same time, basically. And once we send it, we'll also put it in par with itself. So we'll get the same effect of like having effectively infinitely many copies. The encoding is a little bit strange in the sense that if you were to actually program it, it would just like run off, you know, to infinity. Basically, it would evaluate it eagerly. So it's maybe not the best way to handle it, but it's certainly a way to handle it. But I haven't seen how new is dealt with in the row calculus, like strictly in terms of row calculus terms.
Well, what, you know, an unforgeable name would have to correspond to some process, right?
Yeah, yeah. I mean, I know the way they do it in rolling is they basically like take, you know, run some crypto function, and now we have like this, you know, output that should never be duplicated as long as we don't duplicate the input, and they take like, you know, current state and all of these different things into account when they run that function to get some sort of, you know, unforgeable process essentially, which is just the output of that hash function, or at least that's what I understand of it. But we don't have any of those primitives in row calc, so I'm not sure where that stuff comes from. I don't know if it's enough to just be able to generate fresh names, or because like unforgeability, I think is you know, not really so much related to row calculus, but I don't know.
I'm thinking of a talk that Greg did where he showed the PyCal.
Yeah.
With a box, and
yeah,
coming out of the box back into the box.
Right.
And then he drew the row calc with this name generator.
Yeah. Yeah, right. Yeah, okay, so just to go back to something we were talking about before, so that name generator, that would be that process of generating the names from the processes, like doing this reflective closure kind of thing, as opposed to in the PyCalculus where you just have a bunch of names to use already, and then you can just go ahead and pick and choose whichever ones you want. Yeah, so I'm not sure how I'm not sure how new is encoded in the row calculus, I guess is what I'm saying.
I guess that would be I mean, there's a process that generates them, so it would represent some process, I guess.
Yeah, I think maybe you can at least get fresh names like fairly easily, and then maybe that's enough to just be able to receive a fresh name or something. Yeah, I'm not really sure.
Right.
Yeah, maybe you can like deconstruct it back into like a more simple term using the lambda calculus rules or whatever the situation would be. Like if you have some term, you could just evaluate it until it becomes you know, whatever base it would be, and then give it a name from that. As like the construction of its processes.
Yeah, it's possible. Like there is certainly a way to put together processes that you currently have access to in such a way that you can produce a name that is fresh with respect to all of those processes. So if you were to like take all of the processes that you know and love and then put them in par with one another and then quote that new process that is the par of all of those processes, I think that's enough to get a name that's fresh with respect to those processes. So I think there's a fairly straightforward way of doing that, but like I said, I'm not really sure how that relates to new. We can try to keep pushing on with this stuff though. Yeah, so what are we doing here again? So I know he's giving these two operations of reify and reflect. And so these are going to be similar to quoting. They're going to be, so reify is basically quoting, because we're taking a process, you know, that's our lambda kx business here, and we're getting some name. And so this is essentially just the process of quoting. That's our reifying this particular process. And what is this reflect thing doing again? Why is there a +1 there?
Polynomial +1.
Yeah. Usually the +1 is coming from some sort of like you know, category with one element or something, but I'm not even sure I see how it applies in this case. Yeah, I'm not sure.
Like hard with a 0 or something.
Yeah, it could be something like that. Yeah, I'm not sure, because I was thinking we already had the stopped process in T itself, just from, you know, taking a sum with no terms, but I'm not 100% sure. But
how does this get us reflection? Okay, so reify is the naming process from a process. Reflect is taking that process and giving us a polynomial. That's also a process.
Reflecting is giving us a process. Yeah, it's taking a process and giving us some sort of term, I think, but I'm not totally sure. Oh, okay. So wait, this this TKX is part of lambda, right? Like we had in our definition of lambda, like we have the evaluation, abstraction, application. Then we also have all of these terms T, and then also all of these terms T prime. But point being is that T is contained within this lambda stuff. So we're basically taking a process, a general process lambda, and getting back a specific process. I'm not exactly sure what is specific about that process, though.
What would be the difference between a general process and a specific process?
Oh, just like some like so we have, you know, lambda is like any possible process, and then T is maybe just all of those processes that are like some sort of evaluation or something along those lines. Or
so it's reflect is basically just saying that you can take any process and turn it into a polynomial.
I am not sure, honestly. I mean, I assume that this. Okay, so I think this first equation that's written here is supposed to correspond to this reify thing. So we're basically saying, like, if we take some lambda term of the form like star at T, and then we quote that, then we'll just get back this name at T, right? So I think that's corresponding to this reify operation here. And so I'm assuming this this lambda n dot star n of at T going to T, this is supposed to be this reflection. But I'm not exactly seeing why this is reflection. Maybe it's just this kind of like inverse relationship between the evaluation and the quoting that we're calling reflection.
Yeah, I mean, that's like the application,
Yeah.
the name T, and then you dereference it and you get T.
Yeah. Yeah, I'm not seeing why this is only restricted to kind of like a subclass of our processes, though, because if we're just looking at at t, I mean, t should be able to be any process. Yeah, I mean, even in our, we apply it to names, but names are just a quote of any process.
Well, maybe they show like an example of reflect semantics down below.
Let's see, I don't remember. I think that's more or less where it ends. Oh yeah, it's just got some conclusions that are not like specifically like, here's some examples of the things we're talking about. Well, yeah, either way, maybe we can make some sense of this slide here. Yeah, so he's always talking about this structure function relationship and how this is not reflected in a lot of different areas, but that these computational calculi carry this structure function relationship. And I mean, so my understanding of why he feels all of these things are so important is because of that fact, right? Like this kind of like explicit dealing with structure and function simultaneously instead of as being separate things. Yeah, okay. Yeah, so so he's saying an example of a term that's like K1X is something like sending a process on a name. But I'm not sure I understand why that's an example of something like a K1X. I mean, it's something that only involves one process, but I'm not sure if that's what's meant by this K1 cross X.
Yeah.
And it looks like in this binary interaction, we have some K2 and two X's, and we're using two processes here. I'm not sure if those X's are just for processes or what. They very well may be.
Well, both processes use X.
Yeah.
One listens on X, one sends on X.
Yeah.
So binary interactions. Is it about the channel with process X?
Yeah, I'm not sure. Yeah, I'm wondering if it's because we're just dealing with two processes here. Oh, maybe so this potential for interaction, like the one array term. So it just takes one process, right? And the whole process is the send of Q on X. I was thinking that the process that we're using is just the Q, but I think it's the entire send of Q on X. And so we're taking one process, and it's this send process. And then here for the binary interaction, we're taking two processes. One of them happens to be a send, and one of them happens to be a receive, and they happen to be on the same channel. So we can have some sort of reduction from this. And then, I mean, for something like, okay, so and maybe with this binary stuff, I mean, if we were to have like two sends in par, that would still be an example of a binary term, I think, and but there just wouldn't really be any interaction between those two. So I think he's explicitly showing, an example of this binary like term that does actually have an interaction.
So why is K1 cross X a potential for interaction?
Oh,
or does it once you apply it to something?
Yeah. So I think he's saying potential for interaction because, well, there's only the one process itself. So like a send or like a receive or something along those lines, but they don't have any sort of reduction rules just as a single process. They need another process to reduce with, I think is what he's talking about there.
Yeah. Okay. So this is weird because the cross, the X, before we were using addition with the summation and polynomials to represent par.
Yeah.
And here we're using, well, let's say a cross product or something.
Yeah. So maybe what we should be thinking of here is like for the summation, it's really just like we can have all of these different types of terms. So like the pipe in like a BNF style, whereas this cross here, I think, is literally representing the par operator. So I think this K1 cross X is like one thing in par with itself, but I mean, this is, you know, just a single process, of course. Whereas something like this K2 cross X is like two things in par with each other.
Okay. So the addition operator, what was that again?
So I think the addition operator is more like the pipe in like a BNF. So it's like a coproduct. It's just like we have all of these different flavors of terms, and you can choose whatever one of them you want, basically. So like you can have like a 0 array term or a 1 array term or a 2 array term, so on and so forth, up to whatever n you specify at the beginning.
So it's like a sum type.
Yeah, exactly. A sum type. Yeah, exactly. Yep.
Okay.
Yeah, I forget. There's like 10,000 words to describe each one of these ideas, and I never know which one is the best to use, you know? So like, and usually I'm just thinking about them in my own head, you know, so I'm not like telling other people like, oh yeah, it's a sum type, you know?
Yeah, I feel like I need to learn category theory a little better, because people generally like to use that one to describe like very general notions, and I know Greg Meredith likes to use them a lot.
Yeah, for me, you know, I started what is that guy's name? Bartosz Maluszki. I know Jim was also watching those lectures. Those are really good. That's probably a great place to start, since you already have like a really strong programming background, and he makes like tons of allusions to programming, and they're just really good lectures.
Yeah, I think I've watched like the first 6, and I've been
nice.
Cool. Yeah, I need to finish them. I only got up to like functors, and it's something you have to watch a few times.
Yeah. Oh yeah, definitely.
Right. But now I have to start over again or something.
Wait, what?
I a few weeks ago I did up through functors.
Oh yeah.
And everything was very clear then, but now I have to go back and start over.
Yeah, I'm definitely gonna have to watch the one about Cleasley stuff again. I at the time, it's like, you know, it's one of those things that as you're watching it, it's like, oh yeah, this is so clear. It's so clear. Just like with all of these RCasts, for me, this is how they go. Is like, as we're talking about, it's like, oh yeah, I definitely see this. That's a great idea. Like, this is really cool. And then it's like, oh, what did we talk about? Oh man, I have no idea. Like, I don't even remember anything that we talked about. I don't know. That's how I always feel about everything now.
Yeah.
But yeah, so I think the right way to think about, the one thing I was going to say in terms of category theory that, for me, I felt like was a really big revelation was, that, so you guys are familiar with BNF, right? I mean, like, I always think in terms of like a BNF syntax for defining a grammar, because that's what you use in K framework. It's like, you know, you're defining your data types, and they're basically all sum types essentially.
BNF is basically just like, if you think of it in set theory, it's like the unions and the
disjoint unions.
You know what BNF is, right, Steve?
I've looked it up a couple times. I don't feel like I've got a really good handle on it, but
well, in Rolang you have a process or a name, right, or something like
this
tells you
that's
what.
Not going to be helpful. Never mind. Sorry.
Yeah, so it just tells you what what you have. You can have what like what's a word composed of? Letters. Okay.
It's like a standard form that everything can be reduced to. Like in logic class, you learn how to reduce everything to ands and ors.
Okay.
It's the same thing.
So that's kind of the foundation of what BNF is, reducing it down to simple common elements.
How you generate it.
Right. Yeah, so they talk about these terminals and non-terminals. I don't think it's really all that important to make the distinction right now, but basically a non-terminal is something like, man, I wish there was something better to look at here. This all looks, oh, actually, this is not horrible.
Yeah, because
show them the postal address. That's easy.
Postal, I don't know what you're talking about.
First example was a postal address. Very simple.
Oh.
Right there. Oh, down. Where'd you go?
Oh, here. Okay, I mean, this is, oh, interesting. Okay, so they're defining, wait, so which one are you looking at? You're looking at, oh, right here, this postal address. I see it now. All right, sorry, I was looking on the wrong part. Maybe, hold on a second. Let's start with something way easier, like an integer, right? So they're defining an integer here. And so what they're saying an integer is it's either a single digit, so like 0 through 9, or it's some other integer followed by a single digit. Mm-hmm. So for example, right, like we all know what single digits are, like any integer from 0 to 9, right? Mm-hmm. And so now that we know some examples of integers, we can start building examples of the second thing. So something that would be an example of the second thing would be, well, I need an integer. Well, I know integers are single digits for sure. So maybe let's say like 1 or something. So 1 will be the integer here, and then I can pick whatever single digit. So maybe like a 0. So 10 is definitely an integer because 1 is a single digit and 0 is a single digit. So this is like a recursive construction.
Okay, so that would be BNF in its basic explanation of what the formatting is.
And you would define a digit as being a 0 or 1 or 2. The vertical bar or more.
Yeah, there should be something, more like this also defining the same. Oh, actually, I guess they do technically have the single digits defined right here.
Okay.
Yeah, and so they put them all in quotes because this is like, you're gonna parse exactly the 0. Once you see that 0, it's a digit that we're talking about basically. So you can actually generate parsers from this BNF stuff, which is exactly how K-Framework does it.
Okay.
Yeah, and if you look at the integer example again, or the definition, you can see that the pipe here is the or. Yeah. And putting them together is like the and.
Yeah.
So that goes back to just like the logical construction of it. It's all just ands and ors together.
Yeah.
Oh, okay. So that's what that pipe is. It's an and or an or. Okay.
Yeah. It's not a par.
The pipe is an or.
Yeah.
Oh, it is an or. It's not an and or. Okay.
Yeah, it's really an XOR kind of because, so I mean, we're saying, integers come in 2 flavors. They're either a single digit or exclusively they're an integer followed by a single digit.
Okay.
Yeah.
All right. Helpful. Thank you.
Yeah. So what I was saying is I'm on these slides. So what I was saying is this sum here is really the same. Oh, crap, I keep doing that. So that sum is really the same thing as this pipe here. So it's like an exclusive or, but a generic one because, we have some arbitrary number of things that we're putting together. So we need like a more compact way of expressing that.
Okay.
Yeah.
That makes a lot more sense to me now.
Yeah. Oh, great.
Naturally, I would have thought of plus as like a pipe, but
yeah, it's weird. I mean, they use so many different terms and so many different symbols to represent literally the same idea. But I think the reason that it's a sum in this case is, well, first of all, to make it look more like a polynomial. But specifically because we're talking about functors and categories, and this is a coproduct in functors or categories, and this is how they represent coproducts. Because a product is like, pi, like you would say, like if I have a product of like 10 things, well, most of the time you don't want to write out all 10 things and then like put a little multiplication symbol in between all of them. So you just put like a capital pi basically, and you're like, okay, take a product from, the first term to the 10th term or whatever. This is the same kind of deal, but in the category setting, when they use this sigma, they mean a coproduct.
Okay.
And K, I'm still not totally clear on what K is.
Yeah, I don't know. It's potentially like some sort of context that's provided. I mean, because it's augmenting each one of these terms that we're constructing here, right? So it's just like,
would it be like the functor or something? I don't see where the functor comes into this exactly.
yeah, so he's saying that this whole thing, the TKX, all of that is the polynomial functor that we're starting with. So I mean, he's just using the K as some parameter, and basically the way that K is brought into it. Okay, so maybe this will make it make a little more sense at least. So the bold K as opposed to the non-bold Ks. This K is like a vector of n different things that are the K sub, 1 or 0, wherever we start, I guess K sub 0. So maybe it's a vector of n plus 1 things. So bold K is like the vector, like K0, K1, K2, all the way up to Kn. Yeah, but I'm not 100% sure. So he's keeping it like this to keep it general, but I don't know the reasoning for including this, other than like, well, this is just like a general polynomial to have something along these lines.
Yeah, the functor. So I mean, I forget the exact definition of a functor, but it's basically a mapping between categories.
Yeah.
In this case, like, or say in the Roland case, what would you consider a functor to be? Like, what would the mapping be?
So in the Roland case, what would a functor be? Yeah, so something like, so I think we can really view any of the terms, any of the constructors as functors. So you can think of like the send term constructor as a functor. So what it's going to do, well, okay, maybe that's not the best example because it's going to take a name and a process. But either way, what it's going to do is in the category of, let's say like row calc or something like that, what this send functor is going to do is you're going to give it a name, you're going to give it a process. It's going to combine them or construct them into the term that is the send of that process on that name. And now we have a term that's also in the row calculus. So it's what they call an endofunctor. So it's a functor from that category back to itself, essentially. Well, so I'm not 100% sure that would constitute a functor because there are some other constraints that a functor has to satisfy, like it preserves morphisms and all of that stuff. So I'm not sure what the morphisms would be between the names and the processes to begin with, but
I see that. It's kind of like a constructor that you can apply names and processes to. To build up new names and processes in the same category.
Right. Yeah, exactly.
I mean,
go ahead.
Couldn't you say it maps two categories, preserving the structure?
Yeah, definitely. Yeah, exactly. So it's going to map objects to objects, morphisms to morphisms, in such a way that when we take two objects that have a morphism between them and we map them to these other two objects, that morphism is also mapped between the targets, if that makes sense, right? So we have like two that we begin with. It preserves structure. I mean, that's the most streamlined way of saying what I'm trying to say.
And that's a functor? That was the explanation of a functor? Okay.
Yeah, it's a mapping between categories that preserves the structure.
Okay.
Yeah, I think the big revelation that I had in the video so far is that it's a pattern recognition.
Yeah.
It goes back to the information problem and pattern recognition, relating them
Yeah, that's when he was defining universal constructions in terms of pattern recognition, right? So he was saying like a terminal object is a universal construction, and we can, find a terminal object by basically doing some sort of pattern recognition. I don't remember exactly how he did it for a terminal object, but basically a terminal object is some object that has a morphism, a unique morphism coming from every other object. So, but I don't remember exactly how he did that.
And I sort of relate that to behavioral types.
Yeah.
You're finding a pattern in the evaluation. It's like,
yeah.
Here I don't really get a strong feeling as to what
So I have another notation question on the first line.
Oh, yeah. Sure. Yep.
Okay, so K subscript I is the ith index of the K vector.
Yeah, yeah.
X superscript I, what is that?
Yeah, I think it's that we have I copies of whatever this X thing is. So it seems like X is going to be a process. So I think, so let's not think of like this thing in general. Let's think of like for when I is equal to 2 or something like that, right? We'll have some K sub 2 thing, which, may or may not be super important. But then we'll have 2 copies of X. And actually he did that on this slide here. So this would be an example of the term that I'm kind of describing right now. So this is one way of presenting it. The other way of presenting it is in that more compact form, which would be like, I can't, for some reason when they have super and subscripts, I can't like actually select it, but whatever. I mean, you see what I'm circling here, right?
So, yeah, it's just the notation for cross products, which are like pars. So it's just saying that term has that many par processes.
Yes, exactly. Yeah. And he's even calling it an n-ary, term or interaction or whatever here. And so I'm not 100% sure that the par is absolutely essential, but I guess it's the one. It's certainly a generic construction that we can just take 2 processes, and we can always put 2 processes in par with one another, right? Or if we have 3 or n processes, we can always just put them in par with each other. So I guess maybe that's just the natural choice for this multiplication or whatever that we have here.
So the n here is the I up above.
Yeah, exactly. Yeah, so our I is ranging from 0 to n, whatever that n that you specify is.
And so this, if you like wrote out a polynomial, in fact, maybe we should, just so that everybody's on the same page.
Yeah.
Like, it would be like 0 or 0 and 1 or 0, 1 and 2.
Oh, wait, let me, hold on a second. No, there's a way to make this text bigger. This is what I want. Okay, cool. That should be good. All right, so what are we saying? Oh, this is humongous. All right, that's great. All right, so yeah, what did we want to do? We wanted to write out an example of one of these.
Yeah.
Okay. So we have this T K X thing, right? And we're saying that this can be, well, I don't really have a sigma button on my keyboard, unfortunately. But so it can be a sum of, several different things. So we have like K0 that we start with, and then we can have, so like a 0-ary term, or we can have, like a single, like a 1-ary term, maybe I'll write it like that, or a 2-ary term, and so on and so forth, right? So this is like X, 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 etc. Yeah, so to write an actual example of this, I guess we can just take whatever process we want and put it in this, basically use this X parameter for that process. And so as before, I'm not sure what these Ks are doing for us exactly, though.
Yeah, so I guess you can't, a polynomial is not like a first class concept in Erlang, because there's not really a concept of the co-product.
Yeah.
So like if you were to write this as close to Erlang as you could, it would just be like 0 or, and or is not part of Erlang, or 0 par 1, or 0 par 1 par 2, or 0 par 1 par 1 par 2 par 3.
Yeah.
Right, that would work.
So yeah, I think if we were to just take all of these as like a stopped process, then we could just basically fill these in with ones and not really worry about this K, because I'm not really sure what is allowable here. But we would essentially have a polynomial like this, and maybe this doesn't make sense, but let me write it anyways. So we'd have a polynomial that looks kind of like that. And so like I was saying, the one is usually representing something like just the stopped process itself. And then X could be just whatever process you want to put in there, just alone, not in par with anything else. And then these X's, in general, they can be different things, but they both have to be processes, is kind of the idea. So if we were to write a term like this one, the one really just corresponds to the stopped process. That's really all it is. If we were to write a term...
Because 0 is still a process, but... So, okay. I mean, yeah, so X is any process, but 1 is specifically the nil process.
Yes, yeah, exactly. Yeah, yeah. And yeah, so something like X could be literally any process, right? Like you could put any process you want here. So like send, receive, I guess par is off of the table because that's our multiplication essentially. But then like X cross X would be any two processes you want in par with one another, or at least this is how I'm understanding it. So it'd be like a P1 par, P2 or something like that, where P1 and P2 can be literally any process you want. So like a receive and a send is the example that he gave in the slides. And then, so on and so forth, right? Like for a three array term, it would be like any process P1 in par with any process P2 in par with any process P3. And, we could just do this for as long as we want, basically.
That was a helpful explanation. I've always, whenever I see, X cross X, I'm thinking, a product, they want to, times X times X, but that's not necessarily the case. That X
it is though, because par is our product in, it's the thing that functions as the product in like the row calculus, for example. In the sense that if we restrict ourselves, so if we look at this as our operation, the stopped process will be the unit for that operation. This operation is associative and commutative. It has exactly the same properties as traditional multiplication does. So if we were to look at, the collection of all of our processes and this operation and this process, which will be the unit for that operation, this form is what they call a symmetric monoid, which basically just means that you can literally think of par as a multiplication operator, and stopped process as kind of like the one element or the unit element for that operator.
Ironically.
Yeah, right. At 0 is 1, you know, and pipe is multiplication, but sums are pipes, you know, so you just gotta keep track of what syntax you're actually thinking of.
Yeah, and going back to the BNF form with the integer, where an integer equals a digit or an integer and digit.
Yeah.
Yeah, in this case, the par here is equal to the plus in our example just now.
Yeah.
And the implicit and between the integer and digit on the right-hand side.
Yeah.
That implicit and there is the par in our example.
Yeah, yeah. Yeah, exactly. So they're, you know, kind of saying something along the lines of like, well, they're using these weird braces, but either way, they're saying like an integer. So this is basically just like so integers come in these flavors is basically how I always read this. But the flavors are, it can be a single digit, right? Or it can be an integer followed by a single digit, but we're using the plus as our or basically. And then we're saying, well, it can be an integer, and then, well, we have and, but we're kind of using an X for our and, which is also our par operator. So then digit, just to translate this into the kind of notation that's being used here, right?
So when we say X as an and, that's different from saying X as a product.
I mean, they're really the same thing. Yeah, they're really the same thing. And if you think about it, mod 2, like multiplication and the and operator are literally the same thing, which is, I think, why they kind of use that abuse in notation.
Okay, I'm going to have to kind of just sit and reflect on that.
Well, so we can write out the truth table, right? For and, you can kind of do like, let's see how I want to do this. So and then we need to start with a 0, which is like, you know, true. I don't know. Do you guys use 0 or 1 for true? I don't know if it matters very much.
1.
Right, 1 for true. All right, and I want to take. Let's see how I'm going to do this. So it's 0, and then I need some lines, and then a 1, and then I need some. I don't need some lines anywhere. I do need lines here. Okay. All right. So basically, maybe I should move this out. Well, either way. So if we were to take two zeros or two falses and take the and of those two things, what should we get? So false and false is false.
Okay.
Yeah.
This is enlightening what you're doing now. And I've never knew that, refer to it as, I didn't know this table had a name. So a truth table.
Yeah,
so
this is a truth table.
Yep. So you can take this, go, you know, from and 0, 1, 2, 3, 4, 5, you know, out to 9 horizontally, then 9 vertically, and do your multiplication table. And that's the essence is that you're using and. It's okay. So now I'm going to kind of reinterpret, you know, when I hear and being used, I have it in a different context now.
Well, so what we mean by the zeros and ones in this context is more of like, are you using this particular piece of information or are you not using this particular piece of information? Or at least that's kind of like how I think of it. So something like this product is like, we have to use both pieces of information because it's like the only viable candidate for and, right? It's like, if I want to use integer and digit, like I literally have to use both of them. That's the only way to make a term that's integer and digit. Because if I only use one or the other, like I get kind of like meaningless stuff almost.
Okay.
Whereas or is totally different, right? Like, or I could use, you know, one, the other, or I could use both of them. Unless we're talking about XOR, and then it's like I can literally only use one of them. them. And this is XOR basically.
Okay.
Yeah, and the digits and integers here, they're not actually digits and integers. That's, I guess, why they're wrapped. They're really strings that we're parsing.
Yeah,
so,
and this is probably misleading that I'm also using integers here, because really this is more like true and false. But the point of me doing it as zeros and ones was to show, so like truth tables are usually written in true and false. Sometimes people use mod 2 arithmetic and use zeros and ones for true and false. But the reason I did it was to show that and is literally the product of the two inputs, right? Like if false and true are the inputs, well then 0 times 1 is 0, right? And so you can reproduce all of you can reproduce the entries of the truth table just by multiplying the inputs.
Okay.
But that's not so this is really the interpretation is like as a truth table with true and false values. No relation to the digits that we're actually talking about. So that made it
right. I tell you this, getting these subtle nuances to describing things goes a long way to my overall understanding.
Yeah,
so,
good.
Yeah,
I mean, these are the things that nobody really tells you, and you're just somehow supposed to pick up on your own, through like watching 10,000 different people talk about the same exact ideas,
Mm-hmm. And to illustrate that point, so you have up there symmetric monoid. I watched a YouTube video that was 20 minutes long explaining what a monoid was. And I've been going for months, not really nailing it down what a monoid is. But after watching this 20-minute video by Numerofile or something like that.
Oh yeah,
Numberphile. Yeah. And then it's like, ooh, a symmetric monoid. Let me kind of work on that for a little bit. So
So monoid is basically just like I have some set and an operation. So here's my operation as par, and here's my set, and and also this identity element. And basically, the only thing that I need for it to be a monoid is that I can take any two of these items and put them together. I think there's some associativity as well. So like if I, let me just write this stuff, right? So like I can take some process A and put it in par with some process B, like no issue, right? Mm-hmm. However, if forgot, gedit's not all that great of a text editor. And Atom, you can just, select all of it, or Visual Studio Code or whatever. Okay, either way, I digress, right? Point being is it's associative as a product. So like not only can I just take two elements and put them in par with one another to produce another process, right? Like that's the important part is I take A that's a process, I take B that's a process. When I put them in par with one another, it gives me another process, right? Like this product or this par or this monoid operation or whatever is just a way of constructing more processes from other processes. So like A and B were processes, I put them together, I now have some other process, like no claim on the relation back to A and B, but I have some other process, right? Okay. With the very specific property that if I do this par first and then this par on the outside, well, it actually makes no difference whether I did the par on the right first or the par on the left. So like these are literally the same terms or structurally equivalent or however you want to say that.
Put in an extra equal sign there to be official. So equal.
So like that, yeah.
We
Exactly.
learned about that a week or so ago. Structurally equivalent. Yeah.
Yep. Yeah, right, exactly. So this is even syntax enrolling for structural equivalence, right?
There we go.
So there's that, right? And then also, if we take our unit, this is the same thing as just taking that the first element by itself. And then, I think this is all we need. But I'm also just making too many assumptions here, right? So not only is that the case, but also if I put the unit on the left side, it's also the same thing, right? So I could put the unit on the right, put the unit on the left.
Oh,
What's
yeah.
that?
Oh, sorry. Yeah, go ahead.
Yeah. So without the symmetric part, so I haven't said anything about the symmetric part yet. This is strictly just for a monoid, right? Like how this operation relates to the set that we're talking about. We have this rule for the identity, or the unit being kind of like the identity for this particular thing. Well, okay, it's the unit. If I also say that it's symmetric, well then additionally where the symmetry comes in. So symmetric is going to give it the additional rules of if I take an A impar with a B, well then that's the same as taking a B impar with an A. And then of course I could delete either the left or the right thing here, but we could just leave them both.
Wow. This was very helpful. So expounding on, I knew individually what a monoid was, and I knew what symmetric is, but now combining the two together.
Yeah.
So, okay.
Yeah, exactly. It just means that the arguments are used symmetrically, essentially, right? Like it doesn't matter if you write it from left to right or right to left, they're the same thing.
This is cool.
Yeah.
And you might also hear a commutative monoid.
Yeah. So this and commutative are used kind of interchangeably.
That was okay, because I've been hearing commutative thrown out as well. So, okay, so that was another helpful tip. So I can think of symmetric and commutative as synonymous. Okay.
Yeah, and the reason being because this is the commutative property, right? Like being able to, it's like, 2 times 3 is the same as 3 times 2, right? And that rule is true for any pair of integers and multiple.
Yeah. This is awesome.
Yeah, cool.
I have a question.
Yeah, absolutely.
I've heard of monoids and symmetric monoids, and I understand these definitions. When do we start talking about Cleasley categories? Cleasley. I'd heard of monoids forever, and all of a sudden now I'm hearing about Cleasley categories.
It's funny that you mentioned that, because I was just saying like maybe 30 minutes ago that I totally do not remember the definition of a Cleasley category.
Well, my understanding, it is the category that's associated with all monoids.
Okay.
And but I'm wondering why we don't hear about Cleasley categories more. Is it that when we talk about monoids, we're out of category theory space and into computer science?
I'm not sure, honestly. Let me look up the definition of Cleasley category, because I honestly don't remember. I think that's how you spell it.
And this, it may not even be important. The fact that you don't register it as. I do remember Bartos has a lecture about these, but like I was saying, I don't remember the specific construction. Okay, that's good enough, because that tells me not to spend too much energy on this yet.
Yeah.
What about, do you have it? Could you say anything about the heating rules that Greg talks about? I'm not grokking that. Is it more subtle or something that we don't need to worry about?
Oh yeah. So heating rules have to deal with the evaluation strategy for a term. So this is something that comes up a lot in K framework, actually, because there you're defining all of the syntax for the language that you're building, and you're also defining all of the rewrite rules. So essentially what you need to do is, given some term, like let's say, why can't I select these anymore? Okay, well, either way. So given some term like this, and by term like this, I mean some term that takes 2 processes. Maybe it does something with these 2 processes, but it certainly just takes 2 processes. which we're calling X and X. What the heating rules correspond to is, how do I say this? So the heating rules correspond to taking, it'll be better if I write it. So heating rules correspond to taking some term. So we have, I don't know, let me put some spaces down here. So we have some term like this, right? And by like this, I mean, we have some stuff going on, and then there's like some process that we're going to put here and some process that we're going to put here. The heating rules are something along the lines of taking this term, and the notation they use in K-framework is this. You take that thing and basically turn it into a sequence of evaluation rules. And so what you need to do is first, so if we're going to evaluate this term, so we would need to specify like what exactly is the evaluation strategy. Like, is it strict in either of these arguments or something along those lines? I'll just pretend as if it's strict in both of them. And so essentially what I need to do is once I see a term like this, I'm going to have to turn it into a few things. So actually, let me rewrite it like that. So I'm going to have to turn it into a few things. The first thing that I'll have to turn this into is I need to evaluate the first term. So the way I evaluate the first term is I take it out of its context, and then I form this context that's going to be like a K cross a whole cross an X, basically. And so what this junk means that I just wrote is like, once I see a term like this, if it's strict in this first argument that I have here, what I'm going to do is rewrite this to a sequence of two computations. Those two computations are going to be evaluate whatever was in that position. And then once you've evaluated it, you're going to put it back into this position, essentially.
Okay.
That's what that stuff means. And then we'll do the same thing for the second one in this case, if it's like strict in both of these things. Yeah, so the heating rules have to deal with taking terms out of their context so that you can evaluate them kind of independently of the context. And then people will also talk about cooling rules, and they're exactly the opposite. Like once you've done the evaluation for that process, like whatever it may have been, once you've done the evaluation there, then actually placing it back into the hole that you got it from, essentially.
Oh, neat! I like that. Okay, cool.
Yeah, and they get this notion of heating and cooling rules from Abstract Chemical Machine. I've never read the paper, but I've seen it referenced by like literally every paper on computational calculi that I've ever looked at. So it seems like it's a pretty important idea.
Interesting.
Would you be willing to link that in the Discord?
Yeah, absolutely. Yeah, I'll just write myself a note here.
Yeah, and tying it to the Abstract Chemical Machine, yeah, that's actually what I was looking for. Good.
Yeah.
I didn't even know where to look to, the only mention I found of it on the web was in Greg's paper with Ratastock, where he thanks someone for suggesting that they do it without the heat rules, and I'm thinking, what are they talking about there?
Yeah. I had never heard of these heating and cooling rules until I started doing stuff in K-framework, and you're not explicitly working with them, but you kind of implicitly work with them by declaring the evaluation strategies and all the terms that you're defining. So that's why I was talking about, like, if it's strict in this term, which is, I never remember the right terminology. I don't remember if that's called by value or called by name or whatever, but the way that I always think of it is like, once I've parsed something that looks like this, then how do I deal with it? Well, in K-framework, the way that it's going to deal with it is like, once you have some particular, term, it turns it into a list of computations, essentially. And so like, this is the list of computations that it would turn this thing into if it were strict in this first argument.
And do you think that this terminology comes from the fact that the chemical abstract machine is dealing with thermodynamics, or or?
Yeah, so like I said, disclaimer, right? I've never read the chemical abstract machine paper, so I'm not 100% sure what's actually written in that paper, but I heard a lot of people talk about it, and my understanding is that the big change or the big like perspective change that came about with this chemical abstract machine was thinking about process calculi as chemical reactions, basically. Like we have this like solution of all of these different terms that are floating around, and like they can interact with one another in certain ways, and kind of like the COM rule or something along those lines. And
So
that's
thinking of chemistry as communicating agents.
Yeah, exactly. Yep. Yeah.
Yeah, I hear that a lot for process calculi.
Yeah.
But this is just any computational calculus.
Yeah. Yeah. I think so. Like I said, disclaimer: I have never read the paper, right? But that's kind of like what I've gotten from listening to different people say things about this chemical abstract machine paper.
So the one thing that we didn't really get to recover since the beginning is the actual differentiation or the derivative.
It's talking about I can't select.
Yeah.
It. Oh, I can select it. Weird. All right. Yeah. So, in what sense would you like to talk about that?
Well, so now that I feel like I fully understand the polynomial.
Yeah.
Look at this. Yeah, and I can see what I-1 would mean here is one less process.
Yeah, right.
And then there's also this I outside of the, which I don't really know what that would mean.
I'm also not too sure about what that indicates. Yeah, so I think, so like with the derivative thing, so what I remember of Greg explaining this idea was that, so the derivative is kind of like a way to obtain a context from a term. And in the sense that like when I take a derivative of a polynomial, each one of those powers of my variable just goes down by 1. So he's thinking of that the power going down by 1 as basically like punching a hole. So I no longer have something that I can just like, well, I'm not sure that's the right way to describe it. So I have these things that I can put processes into, but then I now have this hole that I can fill with, I guess, whatever I want. And so he's saying to fill it with names, at least in this, in this line, we're filling the holes with names.
Okay, and that hole is maybe somehow denoted with this external I.
Maybe
on the line above. Yeah.
Yeah.
Yeah, you take out the process. If the I didn't exist, it would just be the same term with one less process.
Mm-hmm. Well, and the KIs would be associated with a different power of X.
Yeah. Okay.
Yeah, so they would like shift to the right or to the left. Either way, they would shift one way, one position. Yeah. So like I think the way that I was understanding it is like whatever power of X we're looking at here. So if it's like 5, then we have some sort of like 5-ary term constructor. So it's going to take 5. You have to put 5 different processes in it to build a term of this type. And this derivative is basically saying, well, like given that 5-ary term constructor, I can turn it into a 4-ary term constructor in the sense that it is the context with, it's a particular context associated to that term constructor. With a single hold context. So it's a single hold context with respect to that term constructor. And so,
so it's a term, K of I would be like still a 5-term current.
Yeah, exactly.
Yeah.
So
5, but it's part of 4 or whatever.
Yeah, exactly. So it's like K sub 5 is waiting for 5 different things, but you've only given it 4 essentially. So you still have 1 position to put something into.
Okay.
Yeah.
Interesting.
Yeah.
And so by multiplying it with the name, the actual derivative with the name, I guess you could use the distributive property here to apply it to all the different summation terms.
Right.
And then, so the name just becomes that 5th process.
Yeah, exactly. Yep.
So it's kind of like making like a generic for something, like if this is a type constructor or a term data constructor, then it's kind of just like having a generic input for one of its fields.
Yeah, right.
Okay. And I guess the use of this derivative is just a way of creating new processes, just a new way of creating new processes.
Yeah, my understanding is that the derivative is a way of taking given term constructors and turning them into context, basically like punching a single hole. And I think Tomislav talks about this guy, Connor McBride, a lot, and he has a paper, something about zippers or something along those lines. I always forget the name of it, where he's literally doing this construction of like taking a derivative of like a data type and then like relating that to a context for that data type. So I think this is an idea. I mean, I don't know who else has studied that that same kind of thing, but certainly Connor McBride is one of those people.
Yeah, you know, a while ago, it was either you or me posted a blog article about like United, like about 0 equals 1 and the application of like graphs to or algebra to graphs.
Wait, so this was a post where?
It's probably in the computational calculi channel. I can find this thing again. Okay. But I'm pretty sure that same guy does have another really good article about what it means to have a derivative in types.
Yeah.
And it might have been something with the zipper, so I wonder if it's a similar thing.
Yeah, I think this is somehow related. I don't know enough about those ideas to say exactly how this is related, but it is somehow related to those ideas.
I thought it related to the change of the functor.
Yeah, I'm not sure what that means, but yeah, definitely. Well, I mean, so that's like what a derivative means in calculus, right? Is like how something changes, but we need a notion of limit to say that. And we don't, or differentials or something. As far as I know, we don't have either of those concepts here. And so this is just like a formal derivative. So we're just kind of abstracting the idea of that rate of change to a more general context and now just saying like, well, we have this construction, which we call the derivative. I remember using this in abstract algebra for different things. I don't specifically remember the result. It's been like 8 years since I thought about that, but I mean, you can, yeah, go ahead.
And I guess you're removing a variable?
Yeah, that's exactly what you're doing. So yeah, it's analogous to just like punching a hole in a term constructor and now having a context that's basically produced from that term constructor. Or at least that's the way that I understand it. So if we were to have like, oh, maybe this I, okay, tell me if this makes sense. So I think this I is basically the number of ways that we can punch holes in this particular constructor. So for example, if we have a binary constructor, there's 2 ways to punch a hole in this. Maybe I'll write them down here, right? So we have, oh, I already sort of have something here. So we have one way. So with a binary thing, we have, you know, some k to whatever. I can punch a hole in the first term and leave the second thing, or I can punch a hole in the second thing. So I think that's why we have that 2 that's there, because there are 2 different ways to you know, knock out one of these terms, if that makes sense.
Yeah, I would think of that as a partial with respect to x1 or a partial with respect to x2.
Yeah, exactly. Yeah, except these x's are identical because they're just you know, variables that can be replaced with like a process or something. But yeah, absolutely, it's like a partial with respect to the first one and a partial with respect to the second one. But I think the fact that there are 2 ways to do this, and in general there are I ways to do it if we have I of these you know, x variables, I think that's why we get this little I in front of all of those terms, right? Because there's really 2 ways to punch a single hole into a binary term constructor, and there's really 3 ways to do it if we have 3 of those term constructors, so on and so forth.
And he does use the notation for a partial there rather than a derivative.
Yeah. I think that is because we also have this parameter k. So we have 2 parameters, right? Like a process parameter x, and then this k, which I think is literally kind of like our term constructors, because it's like a vector of term constructors, right? I think like this k could be, you know, k could be, you know, take 2 names or take 2 processes and put them in par with one another, and that would be like a binary term constructor. So it would need 2 processes to do that.
Gary, are you saying that at symbol is defined as a partial?
Oh, it's a partial derivative.
That's just a derivative when you have more than one variable. You only take derivatives 1 variable at a time.
Yeah.
And so you use the little what is it, a Greek symbol?
I've always called it a partial. I don't like this symbol all by itself. I've just called it partial.
Whereas
it's supposed to look like a D.
If it was
yeah, it's supposed to look like a D, like a derivative, but to me it looks more like I think it's Adidas or Asics or something. I don't know. There's some shoes that have like almost this exact symbol on them. and to me, that's what it looks like.
Well, that was helpful. You know, half of the battle is knowing what the symbols mean. And you know, now when you said it, like, oh, it does look like a D. Okay, so that's you know, signifies derivative.
Yeah, and specifically,
partial.
Yeah, you do a partial derivative if you have a function with more than one, you know, variable parameter. And here we have k's and x's that are parameters, and so we only want to think we only want to take the derivative with respect to x, and that's kind of what this d of all of this junk over dx is all about. Is like x is the thing that we're treating as varying. Now we're taking the derivative with respect to that. K we're going to think of as its constant. Like, we treat it exactly like a constant when we take a derivative.
Yeah, so I mean, now that you say the I is kind of just like, yeah, you could choose any of the I-1 processes.
Yeah.
I wonder if like it would make sense to put I in another like sub-summation, because it really is that it's a co-product of all the different possible ways this could go.
Yeah, right. Yeah, maybe, I'm not, maybe they just didn't feel like complicating the issue that much, I guess. But yeah, I agree, because like these terms are not going to be laid out in exactly the same way. Like this ki will be constant amongst all of them, but it's a different position that was punched out each time. Yeah,
and this notation doesn't really have any way of saying which position
Right. Yeah, we would almost need something like this with like some eyes here or something to keep track of like what position is being punched out. Oh, actually, you know what? There is a notation that people use for that, and it's typically I can't do it in ASCII, but it'll be like an X. I is the variable that I'm talking about. It's like the ith X that I see, and then they'll put a hat over it. So then that means like the ith position was punched out, basically. So there is a notation for it. I don't know why I didn't use it.
But it's not just I that you would want to punch out, because that would always be the last one.
Yeah.
Where it'd be more like you need to introduce a new J.
Yeah, exactly. So yeah. So you would do like an XJ, and then we would have to like sum over the J at that point, you know, and J would go from 0 to I. So J. Oh boy, this looks horrible. So just write it like LaTeX to I, something like that, basically. But this looks atrocious, so I guess that's probably why you didn't do it.
Yeah. So yeah, there's always that balance. Like mathematicians love to just make stuff look pretty, like aesthetically.
Oh,
and
yeah.
To non-mathematicians, it's so hard to read.
Yeah, well, the prettier it looks, probably the more difficult it's going to be to read. Because naturally, the less information that you're including, right? Because you just want to display like the absolute essential stuff. Well, but that's what gets me about, some individuals that write papers will just assume literally everything up until the position that they start from. And it's like, I have the hardest time reading papers like that, because then you have to go find 10 other papers to be even able to understand this one that you're looking at. So yeah. I feel like as an academic that is publishing research papers, you have to do your due diligence and write a little bit about the background and the notation that you're using, because some people don't even define their notation. They've literally just like hit the ground running and never look back. Like, it's awful.
Wow. Yeah, that should become a part of like the standard template, is like a page background,
Yeah, well, okay, and so maybe I shouldn't blame the authors there, right? Because of course, like, everybody wants to get away with saying the least amount possible to communicate their ideas. I guess it's really more the editors that we should blame in those cases, because they should be reading that stuff and say, like, wait a second, you're using this notation and you didn't even say what it is. Like, come on. I get that it's standard notation or whatever, but throw an appendix in there. I mean, like, anything, really.
Yeah.
Isaac, I remember on Discord, you had a question maybe going back a week or two asking, does anyone know what this means or have a definition for such and such? Did you ever find the definition or get that question answered on Discord?
Wait, you're asking me?
Yeah. Back on Discord, going back a week or two, you were asking, does anyone have a definition for such and such? And I'm like, I saw it, and anyway, it was just a point of interest.
I'm trying. I want to say probably I didn't get that question answered. I can't even remember what question I had.
Now I'm going to go back and look to see what it was, because
cool.
Yeah.
I definitely have some questions that I haven't asked on Discord, but I probably should ask. So for rolling, what is the correct notation for select? Like, where do I need to put braces? What do I need to do to get our node to be okay with the select that I try to put into it?
Jim, that's a Jim question.
Let me see. I'll show you what I'm trying to do if I can find it quickly enough. So match, I got match. Match is good. Of course, S is below select. So I want to do something. Oh, dang it! I don't even have. That's not at all what it was supposed to be. Okay, well, I can tell you what I think the notation for select is, and it's not working. Oh, yeah, okay. And then I have another question after this, I guess. I don't even know what this crap is. So select is like, you use the keyword select, right? And then we put all of our different choices in here, and they're all input guarded, right? So I should have some sort of binding, and then it will like be linked with the continuation, basically. So I could say, and I'll probably need to do some new declaration here, but I would say it's a linear bind, and yeah, I don't know, listens at 0 or something. And then I assume that this should be in some sort of braces, just to, oops, wrong braces. And then it has a symbol like this, I think, and this is my continuation, which is maybe like, I don't know, send on send star B on A or something. And then I should just be able to do something else almost identical to this, like whatever I want my listen and continuation to be. Maybe I'll put some different stuff here. If it only listens on one, and it's on this channel now, and I don't know, maybe it's a send of like 1. I don't know. It doesn't really matter what the process is. But I don't think that this parses. Yeah, so it's a syntax error at this point. So it doesn't like that thing. So, okay. So then the only other option really is to put the braces here. And I remember it not liking that option either, but let's see. So I feel like it makes more sense to put the braces around the listen, but I mean, that's a personal opinion, I guess. Yeah, now it doesn't like, I don't know what that doesn't like. Oh, compilation of construct not yet supported. Okay. But this is the intended syntax for a select construction. Maybe I can make this a little bit bigger. Oh, that's so big now. So I guess what I'm asking is, oh man, it's just gonna have these red things everywhere. It's still gonna keep the red things everywhere. So I guess what I'm saying is it's like, so I have some kind of like linear listen. I have, some variables or patterns or whatever. It's a linear listen. I have some channel, which could have some variables, but I would need to do like a new declaration for those variables or bind them somehow. And then I guess I put the process in braces as opposed to this stuff, which is what I was thinking it should be. But it doesn't really matter because it's not even supported yet, apparently. Oh. All right. Well, what was my other question? Oh, yeah. My other question was about the let construct. I don't remember if this ran or not. Yeah, it doesn't like this thing. What is the intended syntax for the let construct? So my thinking was that I had to put, here is like some process variable and here is some process or something. And maybe I want to just like let that thing be that in itself. And it doesn't like either of what I've written at this point. Yeah, so it's strange because the way that I had it, so what I thought should be the syntax is like, you want to do something like let x equal, I don't know, whatever process you want. Like I'm going to use this process a whole bunch, so I need it to just be some variable, and then in whatever complicated process expression that includes this x thing. So I assume that this was the intended well, not syntax, but like this is kind of the intended usage, is that this thing on the left should be a process variable, it doesn't seem like that's the case, because it doesn't like the process variable when I do the process variable. But when I had like this, then it was okay with the star thing and just didn't like this, which seems really strange.
Yeah.
So it has a syntax error at the arrow now, as opposed to at the variable itself, which I think is really weird. But
you know, as far as who you would go to who would know the answers to these. So you could probably count them on one hand. So either like Greg, Archer, Galloway, or Mike Stay. He's a good one. And Jeremy Busk. Those. But it's.
I think I know who that is. Well,
he's with the Pyrofex.
Oh, okay.
Yeah.
All right. I guess I need to. Well, okay. So select, I think, is clear enough. I know what I was doing wrong with that one, but with let, I'm not really even sure what the intended thing is. But like I said, I feel like it makes the most sense to have some sort of process variable here, and then we're just saying like, okay, this process variable is going to represent this process, and now I can write expressions where I don't need to like recompute things every single time. It's just like some variable represents some process at that point.
Right. So how's K framework coming along? You feeling? You said you're making some big progress that you were before you came on the call.
Yeah, I'm pretty happy with some of the progress that I've been making. So it's been so the last time, I guess I don't really need to share my screen right this second, but the last time I presented things, it was like about matching receives that have multiple simultaneous listens. And I kind of had some ideas as to how I was going to do it, but I didn't have any code to like reflect any of my ideas yet. And so now I at least have what I thought was going to be the hard part of the code. I have that done. And so now it's just a matter of like seeing it through to the end and like putting all of the pieces together and making things work. So I thought the hard part was going to be okay. So let me explain the issue with what I call multi receives. So a multi receive for me is it's a receive that has multiple simultaneous listens. So so it's like a join basically. Maybe I should share my screen. So it's like a join. So when I say multi-receiver, multi-rec is usually how I write it. I'm talking about something like, for example, something like this, right? Like for, listening for one variable. This will be like a linear one. Maybe this is like at 0. And I still don't think that syntax is being used, but this is the intended syntax for the simultaneous listens, and then like maybe B, and I'm listening on, at 1 or something like that. And then, I can do whatever I want with A and B. Maybe I just want to like take both of them and make a list out of those names or something along those lines. So something like that would be an example of a receive that has multiple simultaneous listens. So the listens are like these bindings, right? Like, so I'm listening on the channel at 1 for, one piece of information, one process that I'm going to bind to this variable B, or really, I guess, one name that I'm going to bind to this variable B, and then I'll, evaluate it and put it in a list or whatever. And I'm also at exactly the same time listening on this channel at 0 for some name that I'll call A, and then, also evaluate it and put it as the first kind of argument in this list. But either way, the important thing about a receive like this that has like a join is that it atomically reduces with 2 sends at the same time. So it's like one computational step for it to go from this in par with, you know, say like something on this channel at 0 and something on this channel at 1. So I'll just say I'm sending those processes that the channel name represents. So this atomically reduces in one COM event to, well, the substituted continuation. So it would be like 0, 1, that list. And that's one step, and this thing only can you know, reduce in a COM event if both of these things are present at the same time, right? Like it doesn't consume one and wait for another one. It only sees both and uses them, or it doesn't see everything it needs and it doesn't do anything if it doesn't see everything it needs.
Okay.
So this is a little bit complicated to deal with. And I mean, like, we're only talking about 2 here, right? So in general, there can be arbitrarily many of these things. Like I can put n of them there, you know, but what's n? Well, n is whatever number you want it to be. That's a positive integer, essentially. Mm-hmm. So there can be an arbitrary number of these things. At some point, there will also be a mixing of, so this is a simultaneous, you know, multiple listen. So by simultaneous, I mean it only reduces if it sees both of these at the same time. If not, it doesn't. Mm-hmm. There's a different construction. So that's the intended syntax for the simultaneous receive. This is the current syntax that they're using, which I think will be deprecated at some point in time, because this is going to be sugar for kind of like 2 sequential receives. And by that, I mean, it will find this message on the channel at 0 first, consume that from the tuple space, and then it will look for this message on at 1 and consume that one. And once both of them are consumed, then it can, you know, do the continuation resulting from transferring that data or whatever. So the thing is that, you know, so we have simultaneous and we have sequential. You know, joins is probably not the right word, but, you know, listens or receives. And at some point in time, we'll have the mixing of those 2. So we'll have like, you know, maybe I have a couple simultaneous listens, and then I have like, you know, in sequence with some other thing here. I don't really know what to write. I'll just write this. And maybe we don't even use this thing here, and that's fine. But basically what's going to happen is, so since this is a sequential thing, the first part being a simultaneous thing and the second part being like an individual, which, you know, you could think of as simultaneous or sequential. It doesn't really matter. It kind of fits into both categories and also neither at the same time. So it's kind of your choice as to how you interpret it. But basically what's going to happen is, you know, so now this thing is initially looking for both of these pieces of information at the same time, which, you know, in this example, I've currently supplied it with the right information. Let me, I'm just going to take this down a line so we can actually see all of it. And I'm going to take this down a line as well. Okay, cool. And so what's going to happen here is then, what we'll do is first it will look for both of these pieces of information, one on this channel at 0, one on this channel at 1. It will consume them together, and then basically what it will do is, so one COM reduction is going to get us to like a 4. Now we're just doing the last listen, so this is like at 2, and we've done the first thing, so now we have this stuff substituted in. So I think I said it was like a 0, 1 list there, and now we're waiting for this, you know, message on this channel at 2. Once we see a single message on the channel at 2, then we can go ahead and reduce this thing and then actually, you know, perform this continuation process, you know, which is a ground process the way I'm writing it. But of course, this can be something more general. So does that make sense? The difference between like a simultaneous and a sequential.
Yeah, I understood
receive.
that. Mm-hmm.
Yeah, cool. Okay.
I have a question about the simultaneous.
Yeah.
Could we say, if we're looking at the simultaneous compared to the sequential,
Yeah.
could we, instead of saying simultaneous, would it be equivalent to saying these two things in either order,
Yeah.
but this thing only in this order?
So it's as far as I understand, it's a little bit different in the sense that these things definitely can be in either order, but the difference comes in where when we have this sequential listen, as far as I understand it, we will actually consume the data in the tuple space according to the first
Okay, that helps.
bind, simultaneous bind, whatever in our sequential listen. But we won't do that in a simultaneous listen. It's all or nothing, basically.
Gotcha. Okay. Yeah. I had heard that once before, and
yeah.
the consume part was I was missing that. Yeah.
Yeah. The semantics are a little bit different, even above and beyond just like does order matter or not.
Okay.
Yeah. Okay. So okay. All I'm really explaining here is that things are going to get more complicated once we have mixing of sequential and simultaneous listens. Currently, we're just dealing with these simultaneous listens. So we're really just dealing with things like this. But as far as I know, the syntax is still written like this, but we mean a simultaneous listen, this is how we'll ultimately represent that stuff. And so then the question is like, okay, how do so I basically want to know how I do pattern matching for like a receive that has multiple simultaneous listens. And one, thing that comes up is, well, the fact that the order of these binds doesn't matter, it makes it very difficult to do pattern matching on. So there has to be something that we can do. And so what I mean is like, okay, so here I have one multi-receive. Here I have, let's say, here I have another one, and it looks like this. I mean, so basically I just changed the name A to C and changed the name B to D, right? Like these are alpha equivalent terms. I just gave you the explicit, mapping for alpha equivalents. So these are structurally equivalent terms for sure. And so one should match the other. And so then the question is like, okay, if I have, this is the one that I kind of like have as the thing I want to be matched. And this one is the one that I'm saying is like, it might match this thing. I'm not really sure. I need to check basically. So then the question is like, how do you do this check in general, right? So like here, it's very easy to see how they match because, well, I mean, I said it already, right? Like if C is A and if D is B, well, then of course they match. The problem being is that, like we're going to index these variables before they're actually kind of like interpreted as a rolling term. So really we'll see something more like, add x0 and, add x1. Not that this really complicates anything, but we don't even have these names to deal with anymore. It's just like index variables at this point. So then the thing is like, okay, well, first and foremost, right, like certainly there's something about the binds that I need to check, like somehow, do these binds match one another? And then I also need to ask the question of like, okay, well, given that some orientation, some arrangement of these binds will match, what can I say about the continuations? Like they need to match in some respect as well, right? And so here it's clear. I mean, basically what I'm saying is like, I can say that these two processes are going to match one another in a very straightforward way, because all I need to do is basically change A to a C, change D to a B, and then I see clearly that they're literally syntactically the same thing.
Mm-hmm.
However, you know, let's say that, you know, this thing is really the same channel, which is totally fine syntax. There's really no preferred order for displaying these terms or these listens at this point, because we're now listening on exactly the same channel for a single name variable. And so it's still that same substitution will work, right? Like if I use, you know, A for C and B for D, then this second thing is going to be exactly the first thing. But now my question is like, okay, well that one matches, but you know, now what about this one? Does this one still match this one? Because I want to say like, oh, well, clearly I should just like make A, C, and then these binds will match up. And if I make, you know, D, B, then these binds will match up. But then unfortunately I have a mismatch here. But that's not the only way that I can arrange these, right? Like I can arrange these also in this way, right? Like I can take this thing and put it over here as well.
Mm-hmm.
And this is the same exact process. There's no difference, right? They're structurally equivalent to one another.
Right.
But now I actually see that I do have a match here, right? So like if I let D be A and I let C be B in this case, then A and D, they match up, and B and C, they match up. So I do have everything matching in this case.
Mm-hmm.
So the problem comes in where we have multiple different, multiple possible orderings for these binds, because in some sense they're unordered, right? They're like a set or multi-set or something. But they're displayed as a list. And so we need to somehow take them as an ordered thing and not worry about the order. So unfortunately, what that means is we need to take them as a list and then be able to do like any permutation of them. And so my idea was basically like, okay, given that I'm checking, so this is the one that I want to match, right? So this is my to be matched thing. And this is what I'll call the candidate. And so basically I'm saying like, this is the one that I'm trying to check if it matches this one, right? So what I'm going to do is, first of all, the binds need to match in some way, right? And by binds match, I mean like, okay, this bind could potentially match either of these in the following way. So this bind could match either of those in the sense that, well, the channels are identical. Right? In general, I would just need channels to match, but the channels are literally identical. So this one matching, you know, A from @0 or B from @0, well, neither of those are out of the running to be matched by this bind because, well, the channels match. And also what I'm listening for matches on both of them. And so what I mean by what I'm listening for matches is like, you know, let's say, for example, I'm actually listening for, you know, two pieces of information here, like a D and an E or something, right? So I'm actually listening for two names on this channel. Neither of these are listening for two names. So what I would argue is that this bind matches neither of these potential guys, right?
Mm-hmm.
Okay. But in the case that I'm looking at, this could match either one of them.
Mm-hmm.
So what I need to do now is say like, okay, let's assume that it matches the first one. Since it can match both of them, and this is actually true of this one as well, like it could match both of them. Right. So what I want to do is say like, okay, let's pretend this first one matches this thing. If that's the case, then the second has to match the second. There's no other way. Mm-hmm. And let's see if we get what we want in that case, like, you know, kind of pairing them up in that way. And by that, I mean, if A is playing the role of D in these respective processes and B is playing the role of C, like, do we have the same thing? Do we have processes that match one another? Mm-hmm. And we do because of the way that I organized this stuff, but let's, you know, write it the way that it was originally, which was like this. right? And so it's not so straightforward as A matches with C and B matches with D, because we said that wouldn't actually work here. So basically what I need to do is, like, given that I'm trying to match these two binds to these two binds, I want to generate somehow like something that gives me all of the possible matchings, essentially. And so the way that I've done it is I'm using some kind of like nested sets. And so the set that I would get out of this, and I've been calling this the match bind set, right? And this is like the collection of all possible bind matchings. And so it's going to look like this. So it'll look like 0. So I'm talking about this particular bind as like the 0th bind. So this would be like 0 could match with, and now I'll give a set for the rest of the stuff. Oh, and sorry, this is a set that contains what I'm calling index sets, which is basically like, tell me what bind position you're talking about, and then tell me all of the bind positions in the other process that I could match. So in this case, it'd be like a 0 and a 1, basically. Okay, and then the other part of this should be 1 and a set that can match a 0 and a 1, and I'll explain what all of this stuff means. So what this means as being my match bind set is, it tells me, so first of all, it's a set first and foremost. Okay, it's a set that contains what I'm calling indexed sets. So these index sets are basically like, tell me what bind position you're concerned with. So this is the 0th bind position, and this is the first bind position. So tell me what bind position you're interested in. So 0. So I'm talking about this particular bind in my candidate process. And what binds in the to be matched process can it possibly match with? And so like we said, this thing could match with either one of these, right? So I get a 0 from it potentially matching with this one. I get a 1 from it potentially matching with this one, if that makes sense. And then same thing with the other one here, right? Like this first bind in my candidate receive could match with either the 0th or the first bind in my to be matched receive, right? So that's why I have this set 0, 1 and this set 0, 1 for both the 0th and the first bind positions.
Gotcha. Yep.
Okay.
I'm following.
Cool. Sweet. So so this is like my collection of all possible like matchings of binds. Now what I want to do is generate a map which will basically be the permutation that corresponds to all of these possible bind matchings. And so what I mean by that is 0 could either correspond to 0 or it could correspond to 1. So so I would have and I don't know what notation you're familiar with mappings, but I'll use this one, right? So this means like 0 is the key and 0 is the value, right? So what I'm getting out of this first thing is like, that's one possibility for the key that is 0, right? It could either have a value of 1 or sorry, a value of 0, or it could have a value of 1. But there's another possibility. There's also the fact that 0 could be mapped to 1. Okay. So it's not possible in my setup for any of these kind of like individual key value pairs to share a value. And so by that, I really mean that I just want a permutation when I'm done. So I'll complete the 2 maps that are possible here. So 0 maps to 0, 1 maps to 1 is the first possible map. And the second possible map is 0 maps to 1, 1 maps to 0. So what I'm saying is, well, of course the keys are distinct because it's a map, right? So keys have to be distinct. But specifically values are distinct in these maps. Maybe I'll even put a space in between them. So values are also distinct because I want it to be a permutation. I want everything to map to one distinct thing, right? So like, I don't want to have this bind being compared with this one, and at the same time, this one being compared with this one, because this is just not how things work.
Right.
Yeah. So like, I wouldn't be able to do that, right? But that is possible. Okay. even though 1 could be mapped to 0, since 0 is already mapped to 0, 1 is my only possibility at this point.
Right.
Yeah. Okay. And so now from here, basically, I have these 2 possible maps for like how to rearrange these binds. And so now I basically have a way of like taking these mappings and, you know, applying them to like the ordering of the binds. So I'll rearrange the binds according to these mappings. So like, first of all, this one doesn't rearrange anything, right? It sends 0 to 0, 1 to 1. It doesn't do anything. This one is going to swap them, right? It'll send 0 to 1 and 1 to 0. So it'll basically take this one, put it here, right? Take that one and put it in the 0th position. So that's what these maps are doing. And the important thing is I'm basically just keeping track of these binding variables that I have, or patterns, or whatever you want to call them. Because I'm essentially trying to say like, hey, if I want to match this receive up here, then I need to figure out like who's playing the role of A and who's playing the role of B in this particular thing that is my candidate. And so these maps kind of keep track of like who's playing what role in the to be matched receive. So either way, I mean, like in this first one, it's saying C is playing the role of A because 0 is going to 0, and D is playing the role of B because 1 goes to 1. But we can automatically see that that doesn't work out, right? Because I said D goes to B, but then, you know, we would have a B in this first position, and that doesn't match with what we have here. But in this case, right, I'm saying that C is actually playing the role of B, and D is playing the role of A, and this is where we'll actually see a match. So basically, point being, right, is like, so even with 2 of them, you know, we have these 2 possibilities. We have to go through both because neither one is obvious that it works or doesn't. And then what we can do is essentially, so using these maps, right, like rearrange these binding patterns really, and then figure out if any one of these potential rearrangements will correspond to like a match for these 2 processes. And so like this gets super complicated when you have even like 3 or 4 of these simultaneous binds, because if you think about it, I mean, now once you have 4 of them, we're talking about like 4 factorial things. I mean, you know, we're automatically talking about like 20 different combinations that could appear here. Whereas, you know, 2 is easy, right? Like, because 2 factorial is still only 2, so it's not that big of a deal. And in fact, we didn't rule out either case, right? And that's why I have 2 possible mappings between these binds. Yeah, but the second you get up to 4, 5, 6, I mean, it grows exponentially, like the number of possible like rearrangements that can work. So I'm trying to work on a way to eliminate some of these possibilities before I have to generate all of these maps and then apply each one of them, rearranging, and then see that it doesn't work.
Well, is this a case where some, you know, creation of a monoid to create an abstraction that automates that for you or is that beyond, not quite the approach?
So so the thing is, I have to do all of it in K framework, and so in K framework you are defining all of your syntax, right? So like so it looks exactly like the BNF grammar stuff, right? So like for example, here's a function that I'm defining that's going to go from a map, and so this set is basically going to be so with each one of these multi-receives, like I have multiple binds, right? They're arranged in some order already. So what this set is going to be is like, take the 0th bind and say like, okay, that's the 0th bind. And that's kind of like my first element in my set is, I can write this in a better way, I think. Can I? So this set is what I call the bind set, and say the bind set for, the first one, which I'll put a star there and then put a star there. So the bind set for this first one would be, well, this is the 0th bind and this is the first bind, right? So it'll look like, it'll be a set first and foremost. And the 0th bind in this set is A from at 0. And the first bind in this set is B from at 1. So it's going to generate a set like this, where it's basically taking each one of the binds and putting this index for the position that it occurs in, essentially.
Okay. Yep.
Yeah, and so that's this set here, right? Is like what I'm calling the bind set. Mm-hmm. And then it also takes a map, and so I'm calling this function arrange binds. Mm-hmm. It takes a map and a bind set, and it returns a set, which turns out to also be a bind set. And then the way it does it is it's basically going to take this set. So here's a bind set, and it's going to take a map like 0 to 0, 1 to 1, and it's going to look at just the index. And, if it's 0, it'll change it to 0, so not much change. And if it's, 1, it will change it to 1, so not much change either. Mm-hmm. But it would be more interesting if this was the map we use. So if this is the map we use with this bind set, what it's going to do is it's going to rearrange the binds according to the map. So it'll send the 0th bind to the first position. So it'll basically turn this into a 1, and it'll turn this into a 0. Which effectively is saying, like, take this bind and put it in the 0th position, take mm-hmm. this bind and put it in the first position.
Right. Yeah.
Okay. So there's this, terrible construction of basically like you're deconstructing this term and turning mm-hmm. it into this like index set of binds, and then mm-hmm. you're producing all of these like possible mappings that are like you're matching binds, and then now I have to like rearrange the entries in this set so that I can work with them in the order that I want, and it's all just a headache basically. But like I said, I actually have started making progress. So like I can generate these maps now, no problem. I can generate these match bind sets, mm-hmm. bind sets. All of this stuff is going well.
Neat. Well, yeah, you gave a good explanation. I mean, I feel like I'm right there with you now as far as working through the problem.
Yeah, so, cool.
Yeah.
Cool. Yeah, and I'll definitely have some more stuff to show. Well, I hope to at least have some more stuff to show next time as well, and actually have like all of this stuff working, and then like produce an example of like, oh, this thing matches this, and I can run some code and show you exactly how that happens and all that good stuff.
Yeah, I've enjoyed your previous demos of showing how K-Framework was finding the one bind that didn't match, and it just popped right up, and was like, wow, that's going to be handy. So well, cool. Well, hey, Isaac, I appreciate you leading the discussion today.
Yeah,
I think everyone did. Everyone said it was a really good session, and
cool.
Getting a better understanding of that RCast, and thanks for the overview of multiple bind sets. So I'm looking forward to seeing how that plays out.
Cool. Yeah, absolutely. Me too.
All right. Cool. Hey, you have a great day.
Yeah, absolutely. You too.
Okay. Thanks.
See you next time.